Hello and welcome. In this video, I'm going to explore the 8051 timers, and I'll be using the Keil MicroVision IDE for my coding. So introduction. So let's take a quick review or a revision of the 8051 block diagram. Here's the block diagram. First off is the CPU, then the RAM, the ROM, the input-outputs, serial port, and most importantly for this video, we are looking at the timers. So timer 0, timer 1, timer 2. Now the original 8051 has two counters timers. The AT89S52, which is the microcontroller that I'll be using for my video series, has three counters timers. The timers have three general functions: keeping the time and or calculating the amount of time between events. That's basically measuring time. Then secondly, counting the events. We would not be looking at the counting part here, the counters. We'll be focusing mainly on the timers. And thirdly, but not least, these timers are used to generate baud rates for the serial port. And this would be the topic of my next video. Okay, so let's look at how to program the AT51 timers. Now, before we look at the programming part, let's look at the registers that are involved in programming the timer or timers. The first one is the timer mode register, or TMOD. And the TMOD register is used to set the operating modes of the timers. We'll come to the details of this soon. Then we need to look at the timer registers. These are 16 bits wide timers. As I mentioned earlier, the AT89S52 has three timers. They are timer 0, timer 1, and timer 2. And the function of this timer register is to load the timer with the count or value. More details in a few moments. Then last but not least, the timer control register, or TCON. And TCON is used to start or stop the timers. Now, these are the steps that you need to take to program the 8051 timers. So number one, you need to set the timer mode. Number two, you set the timer registers. Then you run the timer, and then you monitor the timer flag bit. So these are the steps that you need to take to program the 8051 timers. Okay, so let's take a look at the timer mode register, or the TMOD register. So the TMOD register is an 8-bit wide register. The lower 4 bits is used for timer 0. The upper 4 bits is used for timer 1. And the TMOD register function is to set the operation modes of timer 0 and timer 1. As mentioned a few moments ago, the lower 4 bits is used for timer 0, and the upper 4 bits is used for timer 1. As you may have observed, that the bits that is in timer 0 is identical to the bits in timer 1. So let's focus on timer 0. So if gate is set to a 1, logic 1, then the timer counter is enabled, and the timer is controlled by interrupt INT 0 or interrupt INT 1. If the gate is set to logic 0, then it's used for internal clocking. if you want to use this as a counter, then you need to set this to a 1. And if you want to use it as a timer, which is our intention in this video, so we need to set this to 0 because we want to use it as a timer. Now, as mentioned earlier, we need to set the mode of operation. So these 2 bits here, M0 and M1, let's refer to this table here. If M0 is a 0 and M1 is a 0, so it operates in mode 0. That is a 13-bit timer mode. If M0 is a 1 and M1 is a 0, then it's operating in mode 1, which is a 16-bit timer mode. And if mode 0 is a 0 and M1 is a 1, then it will be operating in mode 2. That would be an 8-bit auto reload mode. And if M0 and M1 is 1, then it operates in mode 3. That is a split timer mode. Now, in this video, we are concerned with this mode 1. We'll be operating it in the 16-bit timer mode. We'll explain that in a few moments. Now, to program the Tmod, for this example, I'm going to copy 01 hexa to Tmod. What that translates in binary would be this. So I'm not using timer 1, so everything is set to 0. Now, gate is set to 0 because I'm using an internal clock. I'm using this as a timer, so this bit here is set to a 0. Now I want to operate in mode 1, so M1 is set to a 0 and M0 is set to a 1. So this will set this timer 0 to mode 1. Okay, now let's take a look at the timer registers. So first off, let's look at timer 0 register. Remember, the original 8051 has 2 timers, timer 0 and timer 1. So let's take a look at timer 0 register first. It's a 16-bit wide register. Actually, it's made up of 2 8-bit wide register, as you can see here. So this is timer 0 low byte, which is this one here, that's 8 bits, and timer 0 high byte, which is this one here, and we'll label it TH0 for timer high, TL is timer low. So the 0 indicate they are timer 0. Okay, so let's move on to timer 1. As you can see, it's actually identical to timer 0 register. Again, it's a 16-bit wide register made up of 2 8 bits wide register. So this is timer 1 low byte. This is timer 1 high byte. And this is how you would program the timer register. So you would copy a certain value, in this case 3C hexa, to the timer 0 high byte, MOV TH0, hash 03CH. So that will copy this value 3C hexa into this register. And here we copy this value B0 hexa into timer 0 low byte. So in binary, it will be 00111100 10110000. And this is the value in hexa. So it's 3C, this one, and B0. Right? But how did I arrive at this value 3CB0? All right, so let's take a look at calculating the values to be loaded into the timer. Now, the original 8051, I'm going to assume that I'm going to operate my controller at 12 megahertz. So it's 1 divided by 12 mega or 12 million. That will give us 1 microsecond. Now what that means is that the timer is incremented at every 1 microsecond. So every 1 microsecond, the timer will be incremented by 1. Now, if I want to calculate the hex value for 50 milliseconds delay, so it's 50 milliseconds divided by 1 microsecond, which is derived from here. That will give me 50,000 increments. And we subtract this, the 50,000 from 65536. But where did I get this 65536? Remember, the timer is a 16-bit wide register, so it's 2 to the power of 16. That gives me 65536, and this is the maximum increment I can have with a 16-bit timer. So it's 65536 minus 50000. That will give me 15536 in decimal. So these are all decimal numbers. So we need to convert 15536 decimal to the hex value, and that would give us 3CB0 in hexa. I hope that is clear and helpful. Okay, so we'll now take a look at the timer control register or TCON register. Now, the timer control or TCON register is a 8-bit wide register. So the 8 bits here, and the TCON is used to start or stop the timers. It also contains bits that will indicate if the timers has overflow. Okay, here are some more details of the TCON register, and I'm going to focus first of all on TF1, TF0. That is the timer overflow flag. So the TF1 is for timer 1 and TF0 is for timer 0. So the overflow flag TF will be set to 1 when the timer overflows. That means from logic 1s, it goes to logic 0. In the transition from 1s to 0, the TF flag will be set to 1. We will see this in the demonstration later on. Now, the other bits that is most relevant in this video is the TR, timer run control bit. So TR1 is for timer 1, TR0 is for timer 0. What this bit would do is that when the TR bit is set to 1, it will start the timer. And if TR is set to 0, it will stop the timer. So basically, the TR bits will start or stop the timers. And the IE, the external interrupt edge flag, IE1 and IE0, basically this is used by the 8051 to keep track of the edge trigger interrupt only. And then finally we have the external interrupt type control. So IT1 is for timer 1, IT0 is for timer 0. Basically this is set or clear by software to specify falling edge or low level trigger external interrupts. We won't be dealing with these interrupts in this video. Okay, now that we've got the basic registers of the 8051 out of the way, let's look at an example. So in this first example, I'm going to generate a square wave on P1.2, that is port 1 bit 2, and a time delay is generated using timer 0. So let's look at the code. So as usual, I'm starting the code at 0000 hexa. First instruction, as you recall from our previous discussion, that we need to set the TMOD or timer mode register. So in this case, I'm copying 01 hexa into TMOD. That will set timer 0 to mode 1. Now the next two instructions basically will load a value into the timer register. So first thing is to load or copy 3C hexa into timer 0 high byte. And then the second instruction here is to copy B0 hexa into timer 0 low byte. Together, the value 3CB0 will be loaded into the timer register. Now, a few moments ago, I explained how this value has been derived. If you have forgotten, then I would advise you to just go back to the early portion of the video to see how this has been calculated. Now, the next instruction is to set bit P1.2. That means set port 1 bit 2 to 1, call the delay, then clear P1.2. This will set port 1 bit 2 to 0, call the delay, and then jump back to this part of the code, reload the value, and then set the bit, delay, clear the bit, delay, and then repeat. So with this, you will be able to see a square wave on port 1 bit 2. Now let's come to the delay, which is called in the main program. The first instruction in the subroutine of the delay is to set bit TR0. Set bit TR0 will set TR0 equals 1. That will start the timer 0. This bit TR0, as you recall, is from the TCON register or the timer control register. So when you set this bit to a 1, it will start the timer. Now the next bit is this next instruction here basically will monitor the timer 0 overflow flag. Once it will look for a 1 in TF0. Again, this is a bit that's in the TCON register. I'll come to this instruction in a little more detail in a few moments. So next instruction is to clear TR0. Now set bit TR0 will start the timer. Clear TR0 will stop the timer. Right, because that is equivalent to setting TR0 equals 0. So that will stop the timer. Here, that will clear TF0, clear the timer overflow flag. And here, this will return the control back to the main program. Okay, so let's look at this instruction a little closer. So what this instruction would do is jump not bit set. So if the bit is not set to a 1, we keep doing this instruction. So in other words, it will keep doing this instruction here. So it will stay here. Now let's come down to this diagram here. Assuming the timer registers, the 16-bit timer register, has this value FFFE. At that moment, the overflow flag is still 0 because there is no overflow. Now, when that timer flag is incremented from this point to this point where it goes into FFF, which is the maximum value the timer can have, the overflow flag or the TF flag is still 0. But when the next increment happens, that means from FFFF to 0, 0, 0, 0, that would trigger the overflow flag. So TF flag will be set to a 1. And that's how the TF0 is set. Okay, so we are back in the Keil IDE, and I've uploaded the demonstration code here. Just a word before I start. For demonstration purposes, for single step demonstration purposes, I've changed the values here because I like to single step so that it won't take too long to get to the overflow. So I've changed these values here. For the full run, I would put the original back value later on. So for demonstration purposes, I'm going to put FF and FE into T0 high byte and in T0 low byte respectively. So let me just do the clean the targets, build all targets files. Good news, 0 errors, 0 warnings. That's good. So now I go to debug, start the debug session, evaluation mode. That's okay. All right. Right here I've got the port 1 that you can get this in from here. Right, port 1, and then I've got the timer counter that's here. So because I'm using timer 0, so I check timer 0 and this, and the interrupt system, which is this one here. So call it up. Now these two tabs here, let's look at the performance analyzer first. So this is gotten from view, analysis window, performance analyzer, right? So then the logic analyzer also under view and analysis window, logic analyzer. So these tabs are here. Now for the demonstration, I'm going to single step through the program first. So I'm going to use F11 step. Okay, so all right, let's proceed. So F11. So first one, Tmod. Now Tmod could be observed here. All right, Tmod. So I'm setting timer 0 to mode 1. So yep. So 01 hexar is copied into the Tmod. Now these two register timer 0 high byte, timer 0 low byte can be found here. So let's observe that. So 3FF is gone into timer 0 high byte, and then followed by the timer 0 low byte FE copied. All right, now I'm going to set P1.2 to a 1. It's already a 1, so we won't see much. Now I'm going to call the delay. So I'm going to step into the delay. So watch, yep, and then now set bit TR0. TR0 is this bit here. Watch this bit here. So that is now is set. Now this thing here, jump not bit set TF0. TF0 is this bit here. It's just gone from FF to FF. So nothing should happen if I single step until this thing gets, let's see. Right, now there's an overflow, and from FFFF it goes to 00001. So now this TF overflow flag is set, rolls over, then comes out, clear TR0. So watch this, clears it, clear TF, the flag, the overflow flag, clear it, return back to the calling subroutine. Now this will now clear P1.2. Yes, it's cleared. Go back into the delay and it starts over again. So, all right, so that's the single step. Now let's look at this when we do the full run. All right, so let's stop the debug session. Start it again. Right, now I'm going to run. I'm going to do a run now. So we should see this thing, this LED or this P1.2 blink. Right. It's not blinking. That's strange. Oh, sorry, I haven't changed this back to the values, the original values. So stop it. Go back. So let's change this. That should be 3. C, this should be 0. Right. Save it. Clean the targets. Rebuild all targets. Right. Now we're going to go back. Start the debug session. Wait a minute. Okay, now we do a run. Right, now we got it right. So now it's P1.2 is blinking. We check the delay and we can see the average time of the delay. It's about just over a 50 milliseconds. Remember, the values here are calculated for 50 milliseconds. And if you see, the minimum time is a 50 millisecond, and the max time is just over 60 milliseconds. So the average, it's about 50 milliseconds. So that's okay. So now you've seen this. Oh, let's have a look at the logic analyzer. So let's stop it, and you can see the output of P1.2 on the logic analyzer. So we can now start it again, let it update. And okay, so that's it for this demonstration, and hope you enjoyed it. Let's move on to the next part. Okay, so let's look at another example. So in this example, we would like to generate a 1-second delay. This is the starting point of the program. Now, first instruction, set bit P1.2, that is port 1, bit 2 to a 1. Call a 1-second delay subroutine, which is this one here. Come to the details of this in a moment. Then clear P1.2, that is set P1.2 to a 0. Call the 1-second delay subroutine. Then go back and do the whole thing again. Now let's come down to this 1-second subroutine. First instruction, I copy this value 14 hexa into register R3. 14 hexa is actually 20 in decimal. And then call this 50 milliseconds delay. And then check the counter R3, decrement it by 1. Is it 0? No, repeat this 50 millisecond, call again. So once this is done, it will return back to the main program. Now let's go back to this part. This loop here will be repeated 14 hexa. In decimal is 20 times. So 20 multiply 50 milliseconds, that should give us the 1 second. So let's move down to this subroutine. So this is the subroutine, 50 millisecond subroutine. If you observe, this is identical to the one that we have used in our previous example. But let's go over it. So set T mod, the timer 0 into mode 1 by copying this value in the T mod register. Then copy 3C into timer 0 high byte, copy B0 into timer 0 low byte. So that gives us the 3CB0 hexa, which is the value for 50 millisecond. We explained that earlier. So set bit TR0, that will start the timer. And then check the overflow flag. So here is jump when bit not set. So when this is not set to a 1, keep doing it, keep jumping here. But once TF0 equals 1, it will come out this loop, get down to this part here, clear the T0 overflow flag, stop the timer by setting TR0 to 0, and then this will return it to the 1 second subroutine calling routine. Okay, so let's move over to the demonstration. Okay, so I've uploaded the second demonstration code into the Keil IDE. So let's go ahead, go to project, clean the targets, rebuild all targets, go to debug, start the debug session, evaluation mode, click OK, and here we have the port 1 up, timer 0, logic analyzer, and the performance analyzer. So we're going to step this through first. So we're going to set P1.2 to 1. It's already 1, so we won't see much. Yeah, get into the 1 second subroutine. Set R3 to 02. For demonstration purposes, I'm using R02 here. So R3 is 02. Call the 50 milliseconds. Again, for demonstration purposes, I've got FF and FE here. So set timer 0 to mode 1. So watch this bit here. Yep, that's right. And then timer 0 high byte will be FF. Yes. And then timer 0 low byte will be FE. So when I step it, it will increment this, and this next instruction will basically start the timer. TR0 is for stop start. At the moment the status is stop, so when I step it, now it's in run mode and TR0 is set. Here notice the timer register is incremented to FF. So but the overflow flag TF0 is still 0. So when you step it through, ask the question, is TF0 equals to 1? If it's not, stay here. So because this is not set yet, so it will stay here one more time. Now notice that it has gone over to 0001, and the flag, the overflow flag is set. So this now should come out. This will clear the flag, stop the timer, clear the timer, watch this, so it stopped, return to the calling subroutine, which is this 1 second, decrement R3, and then ask, is it 0? It's decremented, it's not 0, call the 50 milliseconds again, T mod set to 1, reset the values, and then set TR0 started again. Is TF0 set? No, stay here. Now it's set, it should come out, clear it, stop the timer, go back to the calling routine. Is it 0 yet? Yes, it's 0. Go back to the main program. Right? That's how it works. You've seen how it works in the single step. Now let's do a run. Now before we do that, let's restore the values that we need So here original value is 14 hexa, and this should be 3C, 3C, and this should be B0, B0, right? So we save it. Any changes that you make to the code, you must save it. So, and then clean the targets, rebuild all targets, and this time I'm going to stop. Yeah, okay. Alright, so now I'm going to run it, and we should see P1.2 blinking. Yeah, it's blinking. And if you go over to the 1 second subroutine, you see the performance analyzer. The average time, it's it's almost 1 second. It's 98, 99 milliseconds. But the max time calculated is 1. The mean time is 1. The minimum. So it's pretty close. All right. So let's have a look at the logic analyzer. It seemed to. Oh, we need to reset this. We need to kill this. P1.2, 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 highlight, we want the digital bit, so we want, okay, we will have a red, and close it. So here we are. Alright, so we are getting the signal on P1.2 with the logic analyzer, and the performance analyzer tells us it's 1 second delay that we've got. Okay, so I do hope that it's clear and you enjoyed the demonstration. So that's the end of the demonstration here. Okay, so we've come to the end of this video. The code that I've used for the demonstration can be found in the link given in the description. All right, okay, so thank you for watching, and see you in the next video. Bye.